Let me be honest with you. You think you understand things, but most of what you carry in your head is just labels, words. They sound impressive. They shut down questions. They give authority without earning it. But if you strip the language away and nothing meaningful remains, then the understanding was never there. It was decoration, a costume worn by ignorance to look intelligent. Here's the uncomfortable part. Most education systems reward this behavior. You're taught to recognize the right answers, not to wrestle with the problems. You're trained to pass tests, not to challenge assumptions. So you grow up believing that knowing the correct terminology means you know the subject. It doesn't. It just means you've been exposed to it. Real understanding begins where memorization fails. It begins the moment you ask a question that doesn't have a clean answer. It begins when you try to explain an idea in simple terms and realize you can't. That moment of failure is not a sign that you're stupid. It's proof that you're finally touching the edge of what you don't know, and that edge is where thinking actually starts. The mind loves certainty because certainty feels safe, but certainty is often a shortcut, a way to stop investigating. The moment you become emotionally attached to an explanation, you stop testing it. You defend it instead. You look for agreement rather than evidence. And slowly, without noticing, curiosity is replaced by belief. Belief is easy. Understanding is hard. Understanding demands humility. It requires you to accept that your current explanation might be incomplete or wrong or useful only in limited situations. It forces you to separate what you wish were true from what actually survives contact with reality. That process is uncomfortable, which is why so few people commit to it. Instead, they lean on authority. Someone famous said it. A book stated it. A teacher explained it. That may be a starting point, but it is never the finish line. Reality does not recognize credentials. It only responds to accurate descriptions. If two explanations compete, the one that predicts outcomes more reliably wins. Not because it sounds better, not because it's older, not because more people repeat it, but because it works. That's the only standard that matters. And this is where most people quietly fail. They never test their understanding. They never ask what would happen if this were wrong. They never try to break their own ideas. They protect them, they decorate them, they repeat them louder. But ideas don't become stronger through protection. They become stronger through pressure. If you can't explain an idea without hiding behind jargon, you don't own it. If you can't answer basic questions without getting defensive, you don't understand it. And if you can't admit uncertainty, you've already stopped learning. The goal is not to sound intelligent. That's a shallow ambition. The goal is to see more clearly. And clarity often looks simple, even obvious, once you finally reach it. Not because it was easy, but because confusion has been removed. So here is the challenge you should carry with you. Whenever you learn a new concept, strip the words away and ask what remains. Ask what it explains, what it predicts, what it fails to explain. Ask where it breaks. Ask how you would know if it were wrong. Do this consistently, and your confidence will shrink, but your understanding will grow. You'll speak less, you'll listen more. You'll be slower to declare certainty and faster to ask better questions. That's not weakness. That's intellectual strength. Because the person who knows the limits of their understanding is far more dangerous, in the best possible way, than the person who merely knows the right words. And until you learn that difference, you don't understand reality. You just recognize its names. Certainty is often the enemy of truth because the moment you become absolutely sure, you stop looking. You close the door, not because you've reached the end of understanding, but because certainty feels comfortable. It gives the mind a place to rest. And when the mind rests, inquiry dies. Truth is not offended by questions. False ideas are. That alone should make you suspicious of anything that demands loyalty instead of examination. Real understanding invites pressure. It survives doubt. It improves when challenged, but certainty behaves differently. It protects itself. It resists testing. It treats questions as threats rather than tools. Most people don't realize when certainty takes over because it disguises itself as confidence. Confidence sounds strong. It feels decisive. It's rewarded socially. But confidence without continuous testing is just frozen thinking. It's an opinion that stopped evolving. The world does not work that way. Reality keeps changing, or at least revealing new layers of itself. Explanations that once worked may fail under new conditions. Ideas that were useful approximations can become misleading if treated as absolute. Truth is not a trophy you win once and keep forever. It's a process, an ongoing conversation with reality. Certainty interrupts that conversation. When you're certain, you stop asking why and start saying because. You stop listening for signals that contradict you. You reinterpret evidence to protect your belief instead of adjusting your belief to fit the evidence. That's not understanding, that's maintenance. And the most dangerous certainty is not loud arrogance. It's quiet confidence, the kind that never feels the need to question itself, the kind that says this is how it is and moves on. That mindset blocks discovery not by force but by satisfaction. History is full of ideas that were once held with absolute certainty and later collapsed under simple observation. They didn't fall because people were stupid. They fell because people were convinced they were finished thinking. Every major correction in human understanding began with someone saying, "I'm not convinced," or "something doesn't fit." Those statements don't come from certainty. They come from doubt. Doubt is not the opposite of knowledge, it's the engine of it. Doubt creates movement. It keeps ideas flexible. It allows you to hold explanations lightly, ready to replace them when better ones appear. Without doubt, learning becomes memorization and progress becomes repetition. But doubt is uncomfortable. It leaves questions open. It resists closure. That's why certainty is attractive. It offers psychological relief. It lets you stop struggling with uncertainty and declare victory. The problem is, truth doesn't care about your comfort. Nature doesn't adjust itself to match your beliefs. It doesn't reward conviction. It rewards accuracy. And accuracy requires constant adjustment. The moment you believe your explanation is final, you stop making those adjustments. This is why the smartest thinkers are often the least certain, not because they know less, but because they see more. They recognize the gaps. They understand the assumptions hidden inside their explanations. They know where their models work, and where they don't say, "This is the truth." They say, "This works so far." That small difference changes everything. Certainty turns ideas into identities. Once that happens, questioning the idea feels like a personal attack. Evidence becomes an enemy. Criticism becomes disrespect. And truth becomes secondary to self-protection. At that point, learning is no longer the goal. Winning arguments has nothing to do with understanding reality. If you want to get closer to truth, you have to make peace with uncertainty. You have to accept that your current understanding is provisional, useful perhaps, effective maybe, but never final. That doesn't mean you drift without conclusions. It means you hold conclusions with humility. You use them, test them, and remain willing to abandon them when they fail. Certainty shuts down that flexibility. It replaces curiosity with defense. It trades exploration for stability. And while stability feels good, it quietly erodes the very thing that led you to understanding in the first place. So the real danger of certainty is not that it's wrong. It's that it prevents you from discovering when it is. The truth does not require you to believe in it. It requires you to keep checking. Authority does not equal correctness, and confusing the two is one of the fastest ways to stop thinking. The moment a statement is accepted because of who said it rather than why it works, understanding takes a back seat. Titles replace testing. Reputation replaces reasoning. And slowly, without noticing, judgment is outsourced. Authority feels efficient. It saves time. You don't have to struggle through uncertainty or verify claims yourself if someone important has already spoken. That shortcut is tempting, especially in complex subjects where the effort required to check things feels overwhelming. But convenience is not truth, and mental laziness has never produced. Insight, reality does not recognize rank. It doesn't care about degrees, awards, or confidence. If an explanation is wrong, it will fail no matter who proposed it. If it's right, it will work even if it came from an unknown voice. Nature does not negotiate with authority. The danger begins when respect turns into obedience. Respect is reasonable. You listen carefully to people with experience. You consider their ideas seriously. Obedience is different. Obedience means suspending your own judgment. It means accepting conclusions without understanding the reasoning behind them. That's not learning, that's submission. Many people mistake disagreement with disrespect. They think questioning an expert is arrogance. It's not. Refusing to question is negligence. If an idea is solid, it will survive scrutiny. If it collapses when questioned, authority was the only thing holding it up. History is a record of authoritative certainty being corrected by careful doubt. For long periods, confident experts were wrong, not because they lacked intelligence, but because they trusted established answers more than observed reality. Progress didn't come from louder credentials. It came from people willing to check. Authority tends to protect itself. Once a system of ideas becomes institutionalized, challenges are treated as threats rather than opportunities. Dissenters are dismissed, not evaluated. But truth doesn't advance by consensus. It advances by correction. The most reliable thinkers understand this. They don't ask who said it. First, they ask, how do we know? They care less about pedigree and more about evidence. They don't reject authority automatically, but they never surrender to it either. Blind trust creates fragile knowledge. It works only as long as no one tests it. The moment reality pushes back, the cracks appear. And when that happens, people who relied on authority instead of understanding are left confused, angry, or defensive. Understanding requires ownership. You must be able to trace an idea back to its foundations, see its assumptions, and recognize its limits. If you can't do that, then the idea isn't really yours. You're carrying it for someone else. This is why authority should guide curiosity, not replace it. Experts can point you toward useful questions, proven methods, and past failures, but they cannot think for you. The moment they do, learning stops. There is also a subtle arrogance hidden in blind obedience. It's the belief that someone else has already done all the necessary thinking, so you don't have to. That assumption is not humility, it's avoidance. True humility is acknowledging that no one is infallible, including the most respected voices in the room. It's recognizing that expertise increases reliability, not certainty. Even the best explanations are approximations, waiting to be improved or replaced. Authority becomes dangerous when it is treated as a shield against criticism. When someone says, "Trust me," instead of showing their reasoning, that's a warning sign. Truth does not need protection from questions. If you want to get closer to reality, learn to separate respect from acceptance. Listen carefully. Examine thoroughly. Agree conditionally. Disagree respectfully. And always reserve the right to change your mind. Because the moment you stop questioning authority, you stop participating in the search for truth. You become a spectator in someone else's understanding. And reality will eventually remind you that it never asked who was in charge. Questions are more valuable than answers because answers have an expiration date and questions do not. An answer can feel solid, complete, and satisfying, but that feeling is often an illusion. It gives the mind closure, and closure is where curiosity quietly dies. A good question, on the other hand, refuses to let you rest. It keeps pulling at the loose threads of your understanding. It exposes gaps you didn't know were there. And that discomfort is not a flaw, it's the signal that real thinking has begun. Answers are attractive because they feel like progress. You ask something, you receive a response, and your brain registers completion. But most answers are temporary solutions to deeper problems. They work within a limited context under certain assumptions at a particular level of detail. Treat them as final and they become obstacles. They stop you from noticing when conditions change or when the explanation no longer fits reality. A question does the opposite. It keeps the system open. When you ask a serious question, you are admitting that your current understanding is incomplete. That admission is powerful. It creates space for learning. It allows new information to enter without being filtered through the need to be right. A question doesn't demand loyalty, it demands exploration. Most people are trained to value answers early in life. School rewards correct responses, not interesting questions. Exams measure how well you can reproduce what's already known, not how deeply you can interrogate it. Over time, this trains the mind to chase closure instead of clarity. The habit becomes automatic. Get the answer, move on. But moving on too quickly is how shallow understanding survives. An answer can stop a conversation. A question can open 10 new ones. That's why progress, real progress, comes from questioning what seems obvious. Every major shift in understanding started with someone refusing to accept an answer that everyone else was comfortable with. Not because they wanted to be difficult, but because something didn't sit right. Questions are dangerous to weak ideas. That's precisely why they matter. If an explanation collapses under a simple question, it was never strong to begin with. Strong ideas don't fear questions, they depend on them. Each challenge refines them, sharpens their boundaries, reveals their limits. Without questions, ideas stagnate. They become slogans rather than two. Answers often create the illusion of mastery. You hear an explanation, you can repeat it, and suddenly you feel informed. But repetition is not understanding. Understanding shows itself when you can navigate unfamiliar situations, when you can predict outcomes, when you can recognize where an explanation applies and where it fails. Questions train that ability. Answers alone do not. There is also a deeper reason questions matter more. They keep you honest. An answer can be memorized without being examined. A question forces engagement. It requires you to confront uncertainty directly. It exposes how much of your confidence is borrowed. When you can't answer your own question, you are faced with a choice. Pretend you understand or admit that you don't. That moment separates performance from thinking. Most people choose performance. They collect answers like trophies. They quote them, defend them, build identities around them. And once an answer becomes part of who you are, questioning it feels like self-destruction. At that point, learning stops, not because there is nothing left to learn, but because curiosity has been sacrificed to self-protection. Questions don't let you hide that way. They strip away certainty. They force humility. They remind you that understanding is provisional, that explanations are tools, not truths carved into reality. This doesn't mean answers are useless. They are necessary, but they are not the destination. They are checkpoints, temporary resting places before the next question appears. The mistake is treating them as final. A mind focused on answers asks, what is the correct response? A mind focused on questions asks, what's really going on here? That difference changes everything. When you value questions, you listen differently. You notice inconsistencies. You pay attention to what doesn't fit. You become comfortable saying, I don't know yet, without feeling diminished by it. That comfort is not ignorance. It's intellectual maturity. The most dangerous phrase in thinking is that's settled. Nothing important ever truly is. Reality is too complex, too layered, too subtle for permanent closure. Every explanation is an approximation. Every model leaves something out. Questions keep those limitations visible. Without questions, answers harden into dogma. With questions, answers remain flexible, useful, and alive. So if you want depth, stop chasing closure. Stop collecting conclusions as if they were proof of intelligence. Start cultivating questions that make you uneasy. Questions that challenge what you think you already know. Questions that don't resolve quickly, because answers may make you sound informed, but questions are what actually move you closer to understanding. If you can't explain it simply, you don't understand it, and no amount of confidence, credentials, or complex language will change that. Complexity is often mistaken for depth, but more often than not, it's camouflage. It hid. There's gaps in understanding behind impressive words and long explanations that sound intelligent while saying very little. When someone truly understands something, they don't need to protect it with confusion. They can walk straight through it clearly, step by step, without getting lost. Simplicity is not about dumbing things down. It's about stripping an idea to its core and seeing what actually holds it together. That process is brutally honest. It exposes every weak assumption, every borrowed explanation, every place where you've been pretending to understand instead of actually thinking. That's why people avoid it. It's far easier to repeat a complicated explanation than to build a simple one from scratch. When you explain something simply, you are forced to confront reality. You can't hide behind jargon. You can't lean on authority. You can't say, it just works that way and move on. You have to answer basic questions. What is happening? Why does it happen? What would happen if it didn't? Those questions are unforgiving. They don't care how educated you are. They don't care how many books you've read. They only care whether your explanation actually makes sense. Most people don't fail at understanding because the subject is too hard. They fail because they stop at the first explanation that sounds reasonable. They accept a description instead of building a mental model. They memorize conclusions without understanding the machinery underneath. As long as the explanation feels satisfying, they move on. That satisfaction is the trap. Real understanding feels different. It's quiet. It's precise. It allows you to predict outcomes and recognize when something doesn't fit. And it gives you the ability to explain the idea to someone else without relying on borrowed language. If you can't do that, you don't own the idea, you're renting it. Simple explanations are difficult because they require you to know what matters and what doesn't. They force you to distinguish the essential from the decorative. That takes work. It requires you to rethink the idea multiple times, each time removing unnecessary parts until only the structure remains. That structure is understanding. People often confuse simplicity with incompleteness. They think that a simple explanation must be missing something. Sometimes it is, but often what's missing is not truth, it's clutter. The mind loves clutter because it feels like progress. More details, more terms, more layers. But progress is not measured by how much you can say. It's measured by how clearly you can see. When an explanation is truly understood, it becomes flexible. You can approach it from different angles. You can explain it to different audiences. You can adjust it when new evidence appears. That flexibility comes from simplicity. Complex, fragile explanations break the moment conditions change. Simple ones adapt. There's another uncomfortable reason people avoid simple explanations. Simplicity makes you AC. Countable. If your explanation is clear, it can be tested. It can be challenged. Others can see exactly where it might fail. Complexity offers protection. It creates fog. In fog, mistakes are harder to spot. That's why simple explanations are often resisted, especially in intellectual environments. They threaten status. They remove the mystery that makes some people feel important. If everyone can understand the idea, then expertise has to be earned through accuracy, not presentation. Understanding something simply doesn't mean you ignore its depth. It means you understand the foundation well enough to build on it. Depth without clarity is not depth. It's confusion stacked on top of confusion. Clarity comes first. Complexity, when necessary, comes later. When you hear an explanation that leaves you more confused than when you started, don't assume the subject is too advanced. Consider the possibility that the explanation is bad. A good explanation increases understanding. It doesn't demand patience or faith. It earns trust by making sense. The discipline of simple explanation is a constant test. It forces you to revisit ideas you thought you understood and ask whether you really do. It exposes intellectual laziness. It separates genuine comprehension from polished repetition. If you want to know whether you understand something, try to explain it without notes, without jargon, and without rushing. If you get stuck, that's not a failure. That's feedback. It's telling you exactly where your understanding ends. And that's valuable information. Because understanding doesn't grow from pretending. It grows from identifying what you don't yet know and working patiently toward clarity. Simplicity is not the end of thinking. It's the proof that thinking is.
You drop a cup. It shatters on the floor. And then you wait. You wait for the pieces to jump back together, fly up into your hand, and become a cup again. You're going to be waiting a long time. This is so obvious that it sounds stupid to even say it. Of course broken cups don't reassemble themselves. Of course spilled milk doesn't flow back into the glass. But here's the thing that should bother you. Why not? No, seriously, why not? Because if you look at the laws of physics, all of them, the laws of gravity, electricity, magnetism, nuclear forces, every single one of them works perfectly well in reverse. Run the movie backwards and the physics still makes sense. A planet orbiting the sun, film it, reverse it, and it's still a valid orbit. The physics doesn't care which direction time goes. Every collision of atoms, every interaction of particles, it all works forwards and backwards equally well. So if all the fundamental laws are reversible, why is the world so obviously not? We remember the past. We don't remember the future. Think about that. We have memories of yesterday, last year, our childhood. But the future? Nothing. Blank. We can guess. We can predict. We can hope. But we don't remember it. We feel like we can affect the future. We make choices. We take actions. We try to change what's going to happen. But the past? It's done. Fixed. You can regret it, you can feel remorse about it, but you can't change it. This difference between past and future is so built into our experience that we barely notice it. But it's strange. It's really strange, because the atoms don't know the difference. And now, you might think there must be some law somewhere in physics that says time only goes forward, some rule that says particles can only move this way, not that way, some fundamental principle that makes the past different from the future. But we haven't found it. After centuries of looking, we haven't found any law that distinguishes past from future. The equations work both ways. So where does the arrow of time come from? Let me show you something. Take a box. Divide it in half with a partition. Put white gas molecules on one side, black gas molecules on the other. Now remove the partition. What happens? The gases mix, obviously. The white molecules drift into the black side, the black molecules drift into the white side, and pretty soon you have a uniform gray mixture everywhere. Now, if you wait long enough, will the gases ever unmix? Will all the white molecules ever spontaneously go back to one side, and all the black molecules go back to the other? Technically, yes. It's possible. The laws of physics allow it. If every single molecule happened to be moving in exactly the right direction, at exactly the right speed, they could all end up separated again. But the chances of this happening are so small, so incredibly tiny, that you would have to wait longer than the age of the universe. Much, much longer. The number of years you'd have to wait has more digits than there are atoms in the observable universe. So it's not going to happen. Or push a heavy block across the floor. It slides, slows down, and stops. The friction between the block and the floor brings it to rest. Now wait. Wait for the block to suddenly start moving again. Wait for the floor to push it back toward your hand. You're going to be waiting forever. The energy of the moving block didn't disappear. Energy never disappears. It transformed. It became heat. The friction warmed up the floor, just a tiny bit. The organized motion of the block, all those atoms moving together in the same direction, became disorganized motion. Atoms in the floor jiggling randomly in all directions. That's entropy. Right there, in a sliding block. The organized motion became disorganized motion. The energy spread out. The information about which direction things were moving got lost in the chaos of random thermal jiggling. Every time you see friction, every time something slows down and stops, you're watching entropy increase. You're watching organized motion become disorganized heat. You're watching the arrow of time in action. Your car brakes. Entropy increases. A ball bouncing lower and lower until it stops. Entropy increases. A pendulum slowly coming to rest. Entropy increases. It's everywhere. It's constant. It's relentless. But why? Why doesn't the block ever slide back? Why don't the gases unmix? Each individual molecule is just bouncing around randomly. There's nothing stopping any particular molecule from going left or right. So why don't they ever all go to one side? It's about counting. It's about the number of ways things can be arranged. Think of it this way. You shuffle a deck of cards. What are the chances that after shuffling, all the hearts are together, all the diamonds are together, all the clubs are together, and all the spades are together? Almost zero. Not because any particular arrangement is forbidden. Any specific arrangement of 52 cards is equally unlikely. But there's only one way to have them perfectly sorted, and there are billions and billions of ways to have them mixed up. So when you shuffle, you almost certainly go from order to disorder. Not because of any fundamental law, but because there are so many more ways to be disordered than to be ordered. And that's entropy. Entropy is, you can think of it as a measure of disorder. But more precisely, it's a measure of how many different microscopic arrangements could produce the same macroscopic appearance. When the gas is separated, white on one side, black on the other, there's only a limited number of ways the molecules can be arranged while still looking separated. But when it's all mixed together, there are astronomically more arrangements that all look the same, gray everywhere. So the gas mixes not because mixing is a law of physics, but because there are vastly more mixed states than unmixed states. It's just probability. Overwhelming, crushing, inevitable probability. Now watch this. The laws of physics don't have a direction, but probability does. Probability says you almost always go from less likely states to more likely states, from fewer arrangements to more arrangements, from order to disorder. And that's where the arrow of time comes from. The past is when there was more order. The future is when there will be less order. We remember the past because our brains record information, and recording information requires order. We can't remember the future because it hasn't been ordered yet. Let me put it another way. Every time you break an egg, you're increasing the entropy of the universe. The egg had order, shell intact, yolk in place, everything arranged just so. The broken egg has less order, pieces scattered, yolk spreading, chaos. Could the egg unbreak? Could all those pieces fly back together and reform a perfect egg? In principle, yes. Every atom could reverse its motion. But the chances are so impossibly small that it will never happen in the lifetime of the universe. So the egg stays broken, and time moves forward. This is profound. Really think about this. The difference between past and future, this thing that feels so fundamental to our existence, it doesn't come from the laws of physics at all. It comes from statistics. It comes from counting. It comes from the simple fact that there are more ways to be messy than to be neat. Every moment of your life, you're riding the wave of increasing entropy. Every breath you take, every thought you think, every action you perform, it all increases the disorder of the universe just a little bit. And that's why time has a direction. But wait, there's a problem. If entropy always increases, if everything always moves toward disorder, then why is there any order at all? Why isn't the universe just a uniform gray soup of randomly scattered particles? Look around you. There are stars, galaxies, planets. There's life. There's you, sitting there with your incredibly organized brain, full of neurons firing in precise patterns. How did all this order come to exist in a universe that's supposed to be falling apart? The answer takes us back to the very beginning, the Big Bang. For some reason, and honestly we don't fully understand why, the universe started in a state of incredibly low entropy, extremely high order. Everything was packed together, organized in a very specific way. And ever since then, entropy has been increasing. The universe has been unwinding, moving from that initial order toward eventual disorder. So when you see a star burning in the sky, you're not seeing order being created from nothing. You're seeing the slow release of the order that was built into the universe from the beginning. The star is spending the cosmic inheritance, you might say. Think about it this way. Imagine you have a giant spring, wound up incredibly tight. That's the early universe, full of potential, full of stored order. And everything that has happened since, every galaxy forming, every star igniting, every planet cooling, every life form evolving, it's all just the spring unwinding. We're living off the low entropy of the past. Now you might ask, if the laws of physics are reversible, couldn't we argue that the future also has low entropy? Couldn't we say that the universe will eventually wind back up again? No, and here's why. Suppose you're looking at a box of gas that's half mixed, some white molecules, some black molecules, kind of swirled together but not completely uniform. Now I ask you, what was this gas doing a few minutes ago? And what will it be doing a few minutes from now? If you assume the mixing happened by accident, by random fluctuation, then the most likely answer is that it was more mixed before and it will be more mixed after. The current partial separation is just a temporary fluctuation, and the gas is on its way back to being fully mixed. But that's not what we observe. We observe that the past had more order and the future has less. The gas was separated before, and it will be fully mixed after. This tells us something crucial. The order we see in the world is not due to random fluctuations. It's not an accident. It's a memory of an initial state of very high order. Suppose you look at one corner of a room and you see some order. Maybe the gas molecules there happen to be arranged in an unusual pattern. If this order came from a random fluctuation, then you would expect the rest of the room to be completely disordered. The fluctuation would be local. But when astronomers point their telescopes at new parts of the sky, parts they've never looked at before, they find order there too. Stars burning, galaxies spinning, the same patterns everywhere. This tells us the order is not a fluctuation. The order is universal. It came from the beginning. So the entire arrow of time, the entire distinction between past and future, traces back to one fact. The universe started with low entropy. Everything else follows from that. Why do we remember the past but not the future? Because memories are records, and records require order. The low entropy of the past allows records to be formed. The high entropy of the future doesn't. The whole structure of our experience, cause and effect, memory and anticipation, birth and death, it all traces back to entropy. The Big Bang wasn't just an explosion. It was an explosion of order, a release of potential. And everything that has happened since, every star, every planet, every life form, every thought you've ever had, is riding that wave of increasing entropy. We don't know why the universe started that way. We don't know what set up those initial conditions. It remains one of the great mysteries. But we do know this: the arrow of time points from low entropy to high entropy, from order to disorder, from the past to the future, and there's no escaping it. Now, people sometimes get confused. They look around and they see order. They see crystals forming. They see plants growing. They see babies being born and developing into complex adults. And they ask, doesn't life violate entropy? Aren't living things becoming more ordered over time, not less? No, life doesn't violate entropy, not even close. Yes, a growing plant becomes more ordered. Yes, a developing embryo becomes more complex. Yes, your brain is an incredibly organized structure. But none of this happens for free. To grow, a plant absorbs sunlight. That sunlight is low entropy energy, organized, concentrated, coming from one direction. The plant uses that energy to build its structures, and in the process, it radiates heat back into the environment. That heat is high entropy energy, disorganized, spread out, going in all directions. The total entropy, plant plus environment, increases, always. You are the same way. You eat food. Food is organized, complex molecules arranged in specific patterns. Your body breaks down that food, extracts the useful energy, builds and repairs your tissues, and in the process, you radiate heat. You exhale carbon dioxide. You produce waste. The order in your body is borrowed. It comes from the order in your food, which came from the order in sunlight, which came from the order in the sun, which came from the order in the gas cloud that formed the sun, which came from the Big Bang. So you are not fighting entropy, you are surfing it. Life is not a violation of the second law of thermodynamics. Life is a particularly interesting way of increasing entropy. We are entropy increasing machines that happen to be conscious. Think about that for a moment. Every breath you take increases the entropy of the universe. Every thought you think, because thinking requires energy, and energy use produces heat, increases the entropy of the universe. Every moment you're alive, you're contributing to the great unwinding. But along the way, along this process of increasing entropy, you get to experience things. You get to think. You get to wonder. You get to love and create and discover. Life is what entropy looks like when it gets complicated. And the order that makes you possible, the low entropy that allows your existence, it's not just from yesterday's breakfast. It traces back through an unbroken chain, back through the food chain, back through the ecosystem, back through the formation of the earth, back through the ignition of the sun, back through the collapse of gas clouds, back through the formation of the first stars, back, all the way back to whatever happened at the beginning. You are connected to the origin of the universe, not metaphorically, physically. The arrow of time that runs through you is the same arrow that runs through everything. The entropy that governs your life is the same entropy that governs the stars. When we study physics, we study the fundamental laws, the equations that govern particles and forces and fields. And these laws are beautiful, they're elegant, they're reversible, but they don't tell the whole story. The laws tell you what can happen. They don't tell you what does happen. For that, you need initial conditions. You need to know where things started. And the arrow of time, the distinction between past and future, comes from those initial conditions, not from the laws themselves. This is a profound distinction. The laws are eternal and symmetric. The world is temporal and asymmetric. The difference comes from history, not from physics. We often think of physics as telling us what the world is. But really, physics tells us what the world can be. The world itself, with all its complexity and history and direction, is one particular realization of those possibilities, one particular path through the space of what's allowed. Why this path? Why these initial conditions? Why this arrow of time? We don't know. Maybe we'll figure it out someday. Maybe we won't. But the question itself, the question of why the universe is the way it is, rather than some other way, that question is part of what makes physics so fascinating. We're not just cataloging facts. We're trying to understand why reality is real, why things happen, why time flows, why we're here at all. Now, some people find this depressing. The universe is winding down. Everything falls apart eventually. Every structure, no matter how beautiful or complex, will ultimately dissolve into chaos. But I don't see it that way. Think about what it means to be alive right now. You exist in this narrow window, this brief era between the ordered past and the disordered future, when complexity is possible, when stars can burn, when planets can form, when molecules can arrange themselves into living things. You are not separate from this process. You are this process. You are entropy increasing in a particularly interesting way. So when I say we're all going to the same place, I mean it literally. Every structure dissolves. Every order becomes disorder. Every complex thing eventually falls apart. Stars burn out. Planets cool. Life ends. Civilizations crumble. Eventually, given enough time, the universe reaches maximum entropy, heat death, equilibrium. Nothing more happening ever again. But don't let that make you sad. The fact that entropy increases, the fact that time moves forward, the fact that everything eventually ends, this is not a flaw in the universe. This is what makes the universe interesting. Without increasing entropy, nothing would happen. There would be no change, no flow, no story, just static equilibrium, forever. The arrow of time is what gives us moments. The march toward disorder is what gives us events. The slow unwinding of the cosmic spring is what gives us everything. You exist because entropy increases. You experience time because entropy increases. You can make choices and have effects because entropy increases. So, yes, we're all going to the same place. But the journey is everything. And right now, you're on it. You are made of atoms that were forged in ancient stars. You are organized by patterns that trace back to the beginning of time. You are conscious in a universe that is mostly not. And for this brief flicker, this tiny window between the ordered past and the disordered future, you get to be here. The universe is winding down. But right now, in this moment, it's still wound up enough for you to exist, for you to think, for you to ask questions about why anything is the way it is. That's not tragedy. That's something, isn't it? The arrow only points one way, and that's what makes every moment matter.
Space might be finite, a measurable volume, but it has no edge, no end in the way you're imagining it. Imagine a bug, a tiny flat bug living on the surface of a ball. This bug can only perceive 2 dimensions. It can move forward, backward, left, right. But it has no concept of up or down. For this bug, the surface of the ball is the entire universe. There's nothing else. Now, does this bug's universe have an edge? No. The bug can walk in any direction forever, and it will never hit a wall, never fall off, never reach a sign that says, end of space. But wait, is the bug's universe infinite? Also no. The surface of a ball has a definite size. It's measurable. It's finite. So how can something be finite but have no edge? Here's the secret. The surface curves. It wraps around. If the bug walks in a straight line long enough, it ends up exactly where it started, without ever turning around. The bug circumnavigates its entire universe just by going straight. Finite, but unbounded. Limited size, but no boundary. That's the key. Now here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it. Without ever floating up into the third dimension and looking down at the ball, the bug can figure it out from within. How? By doing geometry, by measuring things carefully. Now here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the third dimension and looking down at the ball. The bug can figure it out from within. How? By doing geometry, by measuring things carefully. Let me show you what I mean. On a flat surface, if you draw a triangle and measure all three angles, they always add up to exactly 180 degrees. Always. Every triangle. No exceptions. But on a curved surface, like a sphere, the angles add up to more than 180 degrees. The triangle is fatter than it should be. On a flat surface, if you draw a circle and measure the circumference, it's always a little more than 6 times the radius. That's just how circles work. But on a sphere, the circumference is less than you'd expect. The surface curves, so the circle pinches. The bug can do these measurements. The bug can discover, through careful geometry, that something is wrong with its space, that the rules don't work the way they should, that space itself is curved. And here's the beautiful part. The bug does this without ever leaving its universe, without ever seeing it from the outside. The curvature is intrinsic. It's built into the fabric of space itself. Our universe might be exactly like that. We might be the bugs. Einstein told us that space is curved, not metaphorically, not as a mathematical trick, actually physically curved. The fabric of space, the void between stars, the emptiness you're sitting in right now, it bends. And what causes the bending? Mass, matter, energy. Every star curves space. Every planet curves space. Even you curve space, just a tiny bit. The more massive something is, the more it warps the space around it. So here's the picture. Our three-dimensional space might curve in a fourth dimension that we can't perceive directly, just like the bug's two-dimensional surface curves in the third dimension. We can't see the curvature by looking at it, but we can detect it. We can measure it. And if our space curves enough, if it curves all the way around, then it closes on itself, like the surface of a sphere, but in 3 dimensions. What would that mean? It would mean the universe is finite. It has a definite size, a measurable volume. But it would also mean the universe has no edge, no boundary, no wall. If you got in a spaceship and flew in a perfectly straight line, just kept going and going for billions of years, you wouldn't hit a wall. You wouldn't fall off an edge. You wouldn't reach the end. You'd end up back where you started. Here's the truth. The universe might be finite, but unbounded. Limited, but edgeless. It might have a size, but no border. And this answers the question everyone asks, the question that keeps people up at night. What's outside the universe? Nothing. Not empty space, not darkness, not some other realm. Nothing. Because outside doesn't exist. Think about it. What's outside the bug's universe? What's outside the surface of the sphere? From the bug's perspective, the question makes no sense. The surface is everything. There is no outside. For us, it might be the same. Space-time is everything. There is no outside. The question assumes something that doesn't exist. And now comes the shock. This isn't just philosophy. This isn't just speculation. We can test it. We are testing it. Remember how the bug could detect curvature by measuring triangles and circles? We can do the same thing on a cosmic scale. We can look at the largest structures in the universe. We can measure the angles of giant triangles formed by distant galaxies. We can check if the geometry works out the way it should for flat space. And what do we find? So far, the universe looks very close to flat on large scales. Very close. But very close doesn't mean exactly flat. There could be a tiny curvature that we haven't detected yet. A slight curve that would only show up at scales larger than we can currently measure. If the universe is positively curved, like a sphere, then it's finite and closed. You travel far enough, you come back home. If the universe is negatively curved, like a saddle, then it's infinite and open. It goes on forever in every direction. If the universe is perfectly flat, then it's also infinite. Space just keeps going with no end. But here's what we know for certain. Whether the universe is finite or infinite, it doesn't have an edge. It doesn't have a wall. There's no boundary you can reach where space just stops. Either it goes on forever, or it wraps around on itself. Those are the options. Edge of the universe isn't one of them. Let me say that again because it's important. Space doesn't end. Either it's infinite and keeps going, or it's finite and loops back. But there's no wall, no border, no end in the way your brain wants there to be. The universe is not a room. It's not a box. It's not contained inside something larger. The universe is everything, and outside is not a place. That outside might not exist. You might be wondering, okay, space is curved, but curved into what? If the bug's surface is curved in three-dimensional space, then our three-dimensional space must be curved in what? A fourth dimension? And here's where we have to be careful. We don't need a higher dimension for space to be curved. The curvature is intrinsic. It's a property of space itself, measurable from within, without reference to anything outside. Let me explain what I mean. When we say the bug's universe is curved, we're describing it from the outside. We see the ball, we see the surface wrapping around. But the bug doesn't see any of that. The bug just notices that geometry doesn't work right. Triangles are weird, circles are weird, something is off. The bug discovers curvature through measurement, not through seeing a higher dimension. We're in the same situation. We can measure the curvature of our space without needing to see it from a fourth dimension. We just do geometry on large scales and check if the results match flat geometry or not. Here's the key. Curvature is not about bending into something. Curvature is about geometry being different than expected. That's the definition. A curved space is a space where the rules of flat geometry don't apply. So stop trying to visualize the universe as a balloon floating in some larger space. That image is misleading. There's no larger space. There's just our space, with its own intrinsic geometry, which might be curved. Now, let's talk about something else. Because curvature isn't the only strange thing about space. Einstein told us something even more remarkable. Space and time are connected. They're woven together into a single fabric called space-time. And when we talk about the curvature of the universe, we're really talking about the curvature of space-time. This matters because it changes everything. Here's an example. You probably know that time passes at different rates depending on where you are. A clock on a mountain runs slightly faster than a clock in a valley. A clock on a speeding airplane runs slightly slower than a clock on the ground. These aren't mechanical errors. These aren't problems with the clocks. Time itself runs at different rates in different places. And why? Because of curvature. Mass curves space-time. And when space-time is curved, time flows differently in different locations. Think about what this means. Near a massive object like the Earth, space-time is curved. And that curvature affects not just space, but time. Clocks tick slower near massive objects. Time literally passes more slowly. This has been measured. This is not speculation. Scientists have taken identical atomic clocks, put one on a plane and one on the ground, flown the plane around, and compared the clocks afterward. They're different, by tiny amounts, but measurably different. The clock on the plane experienced slightly less time than the clock on the ground, because it was higher up, further from Earth's mass, in a region where space-time is less curved. But wait, there's more. This curvature of space-time isn't just an interesting fact, it's the explanation for gravity. You were probably taught that gravity is a force, that the Earth pulls on you, that there's some invisible rope connecting you to the planet, yanking you downward. But that's not what's happening. Here's the truth. You're not being pulled down. You're following the natural path through curved space-time. Let me try to make this intuitive. Imagine you're in a spaceship, far from any planet or star. No gravity. You're floating. Now the spaceship starts accelerating. It fires its engines and speeds up. What happens to you? You get pressed against the back of the ship. You feel weight. You feel exactly like you would if you were standing on a planet. Einstein realized something profound. There's no way to tell the difference. If you're in a closed box and you feel weight, you cannot determine whether you're on a planet being pulled by gravity or in a spaceship that's accelerating. The experiences are identical. This is called the principle of equivalence, and it's the foundation of everything. Here's why it matters. If acceleration and gravity feel the same, then maybe they are the same. Maybe gravity isn't a force at all. Maybe what we call gravity is actually the effect of curved space-time. Think about it this way. When you drop a ball, it falls. You think gravity is pulling it down, but actually, the ball is just following a straight line through curved space-time. That sounds crazy, right? How can falling be a straight line? Because in curved space-time, straight lines look curved from our perspective. The ball is taking the most natural path through space-time, the shortest path, the path that any free object would follow. We call these paths geodesics, and in flat space-time, geodesics are straight lines. But in curved space-time, geodesics look curved to us. They look like orbits, like falling, like the motion we associate with gravity. So the Earth isn't pulling you down. The Earth is curving the space-time around it. And you, by existing in that curved space-time, naturally move toward the Earth, not because of a force, but because of geometry. Now watch this. This explains something that puzzled scientists for centuries. Why do all objects fall at the same rate? A feather and a hammer in a vacuum hit the ground at the same time. Why? If gravity were a force, you'd expect heavier objects to experience more pull. But they also have more inertia, more resistance to acceleration. And these two effects exactly cancel. It seems like a coincidence, but in the curved space-time picture, it's not a coincidence at all. Objects aren't being pulled, they're following geodesics, and the geodesic doesn't care what the object is made of. A feather and a hammer follow the same curved path through space-time because the path is determined by the geometry, not by the object. Here's the secret. Gravity is not a force. Gravity is geometry. The curvature of space-time is what we experience as gravity. And this brings us back to the question of the universe. If mass curves space-time and the universe is full of mass, then the universe is full of curvature. Every star, every galaxy, every particle of matter contributes to the overall curvature of space-time. The total amount of matter and energy in the universe determines its overall shape, its geometry, whether it's curved like a sphere or curved like a saddle or perfectly flat. And that geometry determines the fate of the universe. If there's enough mass, space curves positively. The universe is closed. It's finite. And if you wait long enough, it might even collapse back on itself. A big crunch. If there's not enough mass, space curves negatively. The universe is open. It's infinite. It expands forever, getting colder and emptier. If there's exactly the right amount of mass, space is flat. The universe is infinite. It expands forever, but just barely, right on the edge between collapse and eternal expansion. Which one is our universe? We've measured it. We've looked at the cosmic background radiation, the leftover glow from the Big Bang. We've studied the distribution of galaxies. We've calculated the total mass and energy. And the answer is, our universe is very close to flat, remarkably close. So close that it's almost suspicious. But very close to flat leaves room for mystery. There could be a tiny curvature we haven't detected. And even if it is perfectly flat, the question remains, why? Why this particular geometry and not some other? Here's what we know for sure. Space is curved. Mass causes curvature. The geometry of the universe depends on what's in it. And that geometry determines whether the universe is finite or infinite, whether it has a shape that closes on itself or extends forever. The universe is not a fixed stage where things happen. The universe is a dynamic fabric that bends and warps and shapes itself according to its contents. And we're part of that fabric. We curve it, and it curves us. So let's bring this all together, because we've covered a lot of ground, and I want to make sure the picture is clear. Space is curved. The universe might be finite, but without edges. There's no outside. Gravity isn't a force, but geometry. Mass tells space-time how to curve, and curved space-time tells mass how to move. But there's one more thing we need to talk about, and it's the hardest part of all. Our intuition is wrong. Completely, fundamentally, hopelessly wrong about all of this, and that's okay. Here's why your brain struggles with these ideas. You evolved on a small planet, moving at slow speeds, experiencing weak gravity. Your ancestors needed to throw spears at animals, find ripe fruit, avoid predators. They did not need to understand the curvature of space-time. So your brain built a model of reality that works for everyday life. A model where space is flat, where time flows at the same rate everywhere, where things fall because they're pulled by invisible forces, where everything is contained inside something larger. That model is wrong. But it works well enough for surviving on Earth, so evolution kept it. The problem comes when you try to think about the cosmos, when you try to imagine the shape of the universe, when you ask questions like, what's outside? Your brain uses its everyday model and gets nonsense answers. Here's the truth. The universe is not required to make sense to your intuition. The universe is required to be consistent with itself. And it is. The mathematics works. The predictions match observations. The theory holds together. It just doesn't feel right. And that's your problem, not the universe's problem. Now, let me address something that might be bothering you. If the universe could be finite and without edges, if it curves back on itself, what does that actually mean for us? What difference does it make? Well, here's one way to think about it. Imagine you're an astronaut. You get in the most advanced spaceship ever built. You pick a direction and you start flying. Perfectly straight, no turns, just forward forever. In an infinite universe, you fly forever and never return. Every moment takes you somewhere new. Space goes on without end. But in a finite, curved universe, something strange happens. After billions of years of travel, the stars start to look familiar. The galaxies seem like ones you've passed before. And eventually, you arrive back at Earth, right where you started. You circumnavigated the universe without ever turning around, just by going straight. That's what it means for space to be curved and closed. Straight lines become loops. Forward forever becomes back to the beginning. Now, practically speaking, this doesn't matter much for our daily lives. The universe is so large that even if it's finite, it's far too big for us to ever circumnavigate. We'll never build a ship fast enough or live long enough to complete the journey. But conceptually, it changes everything. It means the universe doesn't need an outside. It doesn't need a container. It doesn't need edges or walls or boundaries. It can be complete in itself, self-contained. Everything that exists, existing within a structure that loops back and closes. Here's the key. The question, what's outside the universe, assumes a certain kind of universe. It assumes space is like a room, contained inside something larger. But if space curves back on itself, that assumption is wrong. There is no outside. The question dissolves. It's not that we don't know the answer. It's that the question doesn't apply.
You know what? People hate this answer. They really do. They want there to be an outside. They want there to be something more, something beyond. Their brains crave it. But the universe doesn't owe us satisfaction. The universe is what it is. And part of understanding physics is accepting that some questions are based on false premises. What's outside the universe might be one of those questions. Not a mystery we haven't solved yet, but a question that was never valid to begin with. Now watch this. There's something beautiful about this picture. Something I don't want you to miss. We are tiny, unimaginably small compared to the cosmos. We live on a speck of dust, orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies. And yet, we figured this out. We, the bugs on the surface, discovered that our space is curved. We measured the geometry, we tested the predictions, we built a theory that explains gravity as curvature and describes the shape of the universe itself. We can't see the curvature directly. We can't float up into a higher dimension and look down. But we deduced it through mathematics, through careful measurement, through the power of human thought. That's remarkable. That's genuinely miraculous, that creatures made of atoms can understand the fabric of space-time, that we can ask, what is the shape of everything, and actually make progress toward an answer. Let me leave you with something to think about. We don't know for certain if the universe is finite or infinite. We don't know if it curves back on itself or extends forever. The measurements are close to flat, but close isn't certain. What we do know is that the universe is far stranger than our intuition suggests. The space bends, time stretches, geometry depends on what's in it. The cosmos might be a closed loop with no outside, or an infinite expanse with no end. Either way, there's no wall, no edge, no boundary where space stops and something else begins. The universe is infinite with an end, or finite without edges, or infinite without edges, but never, never a box with walls. Here's the deepest part. When you look up at the night sky, you're not looking at objects scattered inside a giant room. You're looking at matter embedded in curved space-time. Every star, every galaxy is part of the fabric, and the fabric shapes itself around its contents. The universe isn't a container holding things. The universe is the things, and the space between them, woven together, curving and flowing and existing as one unified structure. There is no outside because there is nothing but the universe. It is complete. It is whole. It is everything. I know this is hard to accept. I know your brain wants more, wants an answer that fits into familiar categories, wants to know what's beyond. But sometimes the deepest understanding comes from accepting that certain questions don't have the kind of answers we expect, that reality is structured differently than we imagined, that the universe is under no obligation to make intuitive sense. So, what's outside the universe? Nothing. Not empty space. Not darkness. Not another universe. Nothing. Because outside is not a concept that applies. The universe might be finite. It might be infinite. But either way, it's everything. And everything doesn't have an outside. That's not a failure of knowledge. That's a feature of reality. That's how the cosmos actually is. And we figured that out. Tiny creatures on a tiny planet, looking up at the stars, doing geometry, testing predictions, pushing the boundaries of understanding. We can't see the curvature, but we know it's there. We can't visit the edge, but we know there isn't one. That's the power of physics. Not just collecting facts, but understanding the structure of reality itself. Understanding what questions make sense and what questions don't. Understanding that the universe is stranger and more beautiful than we ever imagined.
Ladies and gentlemen, let me start with a word we all think we understand: energy. We use it constantly. We drink it in cans. We complain about not having enough of it. We talk about good energy, bad energy, and saving energy. And yet, despite how familiar the word feels, energy is one of the most misunderstood ideas in all of science. Tonight, I want to do something very simple and very dangerous. I want to take that word away from you and then give it back in a form that actually makes sense. Here's the first thing you must accept. Energy is not a thing. You can't touch it, you can't see it, you can't put it in a box. If you try to imagine energy as a substance, some invisible fluid sloshing around the universe, you will be confused for the rest of your life. Energy is not stuff. Energy is a number, a bookkeeping number. And that fact alone already tells us something profound about how the universe works. Now, this sounds disappointing at first. A number, that's it? Yes and no. Because this number has a remarkable property. It never changes. No matter what happens, collisions, explosions, chemical reactions, stars being born, stars dying, the total amount of energy stays the same, always, every time. The universe keeps perfect accounts. This principle is called the conservation of energy, and it is one of the deepest truths we know about nature. Not because we proved it, but because every experiment we've ever done has failed to contradict it. Nature could have chosen otherwise. It didn't. Now here's where things get interesting. If energy is just a number, what does it count? It counts the capacity for change. Anytime something happens, anything at all, energy is involved. Motion, heat, light, chemical reactions, life, thought. If something can cause something else to happen, energy is keeping score. Think of energy like money. Money isn't a thing either. It's an accounting system that tracks the ability to make changes in the world. You can store it, transfer it, convert it, waste it. But the money itself doesn't do anything. People do. Energy works the same way. Now let me ruin another comforting idea. Energy does not come in just one form. We give it names: kinetic energy, potential energy, thermal energy, chemical energy, mass energy. But these are not different substances. They are different ways the same number appears, depending on the situation. Like the same amount of money appearing as cash, credit, or investments. Different forms, same total. Here's the rule the universe follows. Energy can change its form, but it cannot disappear, ever. When energy seems to vanish, it hasn't. It's just gone somewhere less useful, usually into heat, the universe's junk drawer. Now pause and think about this. Every machine ever built, every engine, every living organism, every civilization, all of it is about moving energy from one form to another. Life itself is not about creating energy. It's about channeling it cleverly. And here's the twist most people miss. Energy is not conserved because of some mechanical rule. It's conserved because the laws of physics do not change with time. The universe today follows the same rules it did yesterday. That symmetry, time behaving consistently, is what protects energy. Energy conservation is not just a rule, it's a consequence of order. This means something extraordinary. If tomorrow the laws of physics change slightly, energy would no longer be conserved. The universe would become unpredictable, chaotic, unrecognizable. The fact that energy is conserved tells us that reality has a deep underlying stability. But now we must confront the most unsettling idea of all. If energy is always conserved, and everything that happens uses energy, where did it all come from? And even more troubling, what does it mean that you are part of that accounting system? To answer that properly, we need a concrete handle, something ordinary, familiar, almost boring,
because energy only becomes confusing when we talk about it abstractly. When we watch it work, the mystery sharpens. So, let's start with a machine so simple it feels harmless. Imagine a pendulum, a weight on a string. You lift it, let it go, and it swings back and forth. Nothing dramatic, no smoke, no sparks, no equations carved into stone tablets. Now here's the question your intuition answers instantly and incorrectly. You look at the pendulum and think. At the top, it has potential energy. At the bottom, it has kinetic energy. They trade places. That story feels satisfying. It feels like something is moving around inside the pendulum, but nothing is moving except the pendulum itself. The energy isn't hiding somewhere, waiting its turn. There is no little packet labeled potential that jumps into a packet labeled kinetic. What's actually happening is much stranger. At the top of the swing, the pendulum is arranged in a way that could cause motion. At the bottom, it is arranged in a way that is motion. Energy isn't a thing passing back and forth. Energy is a number that stays the same while the description changes. Same system, same total, different bookkeeping. Now let's push this further, because common sense is still clinging on. If energy is conserved so perfectly, the pendulum should swing forever. But it doesn't. It slows. It stops. Eventually it just hangs there doing nothing. So where did the energy go? You already know the answer. Friction, air resistance, heat. But notice what your intuition tries to sneak in. It imagines energy leaking out like water from a cracked pipe. That's wrong. Nothing leaked. The energy is still there, just spread out among too many atoms to be useful anymore. The air warmed slightly. The pivot warmed slightly. The earth warmed slightly. The universe noticed. You didn't. This is the moment where common sense fails most dramatically, because common sense equates not useful with gone. Physics does not. Physics only asks one question: can I still account for it? And the answer is always yes. This was made brutally clear in a famous 19th century experiment by James Joule. Joule took a container of water, dropped weights that turned paddles inside it, and measured the temperature increase. Mechanical motion turned into heat, not metaphorically, not symbolically, quantitatively. Drop the weights twice as far, the water heats twice as much, every time, no exceptions. Energy didn't vanish, it changed what it was doing. This is the core mechanism you must understand. Energy does not care what it looks like, it only cares that the total is preserved. Motion, heat, light, chemical bonds, electrical currents, these are not different substances, they are different languages describing the same constraint. Now let's challenge intuition directly. You feel tired. You say, I'm out of energy. But that's false. You are full of energy. What you lack is accessible energy in a useful form. Your body is a chemical engine. It runs by converting tightly packed chemical energy into motion, heat, and electrical signals. When that conversion becomes inefficient, you feel exhausted, not because energy is gone, but because it's trapped in forms your muscles can't use quickly. The universe didn't take anything from you. It just made conversion harder. This is why engines matter so much in physics. A steam engine, a car engine, a cell, these are not energy creators. They are energy translators. And translation is never perfect. Some meaning is always lost. Some energy always ends up as heat. That's not poor engineering. That's reality. Here's the analogy that usually snaps things into focus. Imagine energy as money, but money that can only be spent in certain stores. You might be incredibly wealthy, but if all your money is locked in a currency no one accepts, you're powerless. Energy works the same way. The universe accepts fewer and fewer currencies over time. And now comes the realization that unsettles people. The conservation of energy is not about motion or machines. It's about consistency. The universe does not change the rules halfway through the calculation. If you run an experiment today or 1 billion years ago, the accounting balances the same way. Energy conservation is not enforced by a cosmic police officer. It happens because the laws of physics are stable in time. If the rules drifted, even slightly, energy would not be conserved, and neither would anything else you rely on.
So when common sense says energy makes things happen, physics quietly corrects it. Energy does not cause change. Energy measures the capacity for change under fixed rules. The rules come first. Energy keeps score. This is why energy feels so fundamental. It's not because it's a substance beneath everything. It's because every possible change must respect it. No loopholes, no exceptions, no negotiations. And that brings us back to you. You don't sit outside this process observing energy flow through the universe. You are one of the allowed pathways energy discovered, a pattern that holds for now. And once you see that, once you really accept that energy is not a thing, but a rule you can't cheat, something subtle happens. The universe starts to look less like a collection of objects and more like a collection of allowed changes. Because energy doesn't tell matter what to do. It tells matter what it is not allowed to do. You can rearrange endlessly, but you must always balance the books. This has consequences that reach far beyond engines and machines. For example, motion. We tend to think of motion as primary, as something basic, things just move. But motion turns out to be negotiable. You can always change your point of view and make a moving object look still. You can ride alongside it. You can redefine your frame. Energy doesn't care. The energy accounting works in every frame, every perspective. That's already a hint that energy is deeper than motion itself. Now let's talk about forces. Forces feel real. You feel gravity. You feel a push. You feel resistance. But forces are not fundamental in the way we instinctively think. A force is just a way of describing how energy changes with position. That's it. If energy depends on where something is, it experiences a force. No mystery, no hidden hands, just bookkeeping again. The universe doesn't push things, it follows gradients in energy. This quietly unifies an enormous amount of physics, gravity, electricity, magnetism, even the forces inside atoms. They all emerge from the same idea, energy arranged differently in space and time. Once you see that, the laws of physics stop looking like a random list of rules and start looking like variations on a single theme. Now here's where the surprise enters. If energy is always conserved, and if it controls what changes are allowed, then energy places limits on reality, absolute limits. You cannot build a perpetual motion machine. You cannot extract infinite work. You cannot rewind the universe to yesterday, not because we lack cleverness, but because the rules don't allow it. This is where physics becomes philosophical, not by adding speculation, but by refusing to. The universe is not just what happens, it is what is permitted to happen, and energy is one of the strictest permissions we know. This brings us to a paradox people often stumble over. If energy is conserved so perfectly, how can anything genuinely new ever occur? How can novelty exist if the total never changes? It feels like a contradiction, but it isn't, because novelty doesn't come from new energy, it comes from new arrangements. The alphabet is finite, the number of books is not. This is why complexity is possible. Stars, planets, life, minds, none of these required extra energy to appear. They required pathways, sequences of transformations that happened to hold together long enough
to build structure. Energy didn't create complexity. Energy allowed complexity. And now let's confront something even more unsettling. If energy accounting governs everything, then causality itself is constrained by it. You can't get an effect without paying the energy cost. You can't get information without dissipation. You can't think without burning fuel. Every thought you've ever had has a thermodynamic footprint. Meaning is not free. Understanding is not free. Awareness is not free. They all cost energy. This doesn't diminish them, it grounds them. It tells us that meaning is not an exception to the universe, it's one of its natural outcomes. At this point, people often ask, so is energy the most fundamental thing? And the honest answer, the only respectable answer is, we don't know. Energy may be fundamental, or it may be a shadow of something deeper, the way temperature is a shadow of molecular motion. What we do know is this: any deeper theory we find must still explain why energy accounting works so perfectly, because reality refuses to let us escape it. And notice something remarkable. We never defined energy by what it is. We defined it by what it does. It constrains, it balances, it limits, it connects. Energy is less like a substance and more like a promise the universe never breaks.
This changes the meaning of understanding. To understand something deeply in physics is not to imagine it vividly. It is to know what cannot happen, no matter how much you want it to. That's real knowledge. So when you ask what energy means, the answer is not poetic, but it is profound. Energy means the universe is consistent. Change is possible, but not arbitrary. Complexity can arise without miracles, and nothing gets a free pass. So now we can finally assemble the whole picture, not as a collection of clever ideas, but as a single working view of the world. Energy, at the deepest level we currently understand, is not a material ingredient added to the universe. It is a constraint on change. It is the quantity that must remain constant, no matter how wildly the universe rearranges itself. Every law we trust, every equation that survives experiment, respects that constraint. This already tells us something concrete and non-negotiable. The universe is not free to do just anything. If a process violates energy conservation, it does not merely seem unlikely, it does not exist. Full stop. This is why physicists take energy conservation more seriously than almost any other principle. Entire theories have been discarded, not because they were inelegant, but because they failed to conserve energy. Even relativity and quantum mechanics, radical as they are, were built to preserve it, not replace it. We also know something very specific about why energy is conserved. In modern physics, conservation of energy arises from a deep symmetry. The laws of physics do not change with time. An experiment performed today will behave the same way tomorrow or 1 billion years from now. That temporal stability is not an assumption. It's an observed fact, tested constantly. If the laws of physics drifted even slightly with time, energy would not be conserved. The universe would gain or lose energy without explanation. The fact that this does not happen tells us that time itself has a remarkable uniformity built into it. That is not philosophy. That is measurement. Now let's be precise about what energy actually tracks. Energy is not a cause. It is not a force. It is not an agent. Energy is a scalar quantity that assigns a value to the state of a system. That value determines which changes are allowed and which are forbidden. Systems naturally evolve toward states where energy is more evenly distributed, because those states are overwhelmingly more probable. This is why heat flows from hot to cold, why friction exists, why engines have efficiency limits, why time has a direction. Not because the universe prefers disorder, but because there are simply more ways for energy to be spread out than concentrated.
We also know something else that matters enormously. Energy conservation does not mean nothing truly happens. It means nothing happens for free. Every increase in structure requires energy to be concentrated somewhere, and that concentration must be paid for by dispersing energy elsewhere. This is why every act of creation is also an act of waste. Every star, every organism, every idea is accompanied by heat leaking into the surrounding universe. Life does not violate this rule. Life survives because it obeys it more cleverly than its surroundings. Now, what don't we know? We do not know why the universe began in a state where energy gradients existed at all. We do not know why there was something like usable energy instead of a perfectly uniform, inert equilibrium. We do not yet know whether total energy of the universe is exactly zero, positive, or even definable in a simple way at cosmic scales. We also do not know whether energy is truly fundamental, or whether it emerges from a deeper description, perhaps one based on information, geometry, or quantum structure. These are open questions, real ones, active ones. Energy conservation is not the final word. It is the rule that every deeper theory must still explain. And now, here is the synthesis that matters. Energy tells us that the universe is not arbitrary. It is constrained, consistent, and legible. It tells us that change is possible, but only along permitted paths. It tells us why complexity can arise without miracles, and why permanence is never guaranteed. And most importantly, it tells us something about our place in the story. You are not an exception to physics. You are not outside its accounting. Your metabolism, your memory, your thinking, all are physical processes with measurable energy costs. Thought consumes fuel. Learning leaves thermodynamic traces. Meaning requires work. That does not reduce human experience. It anchors it.
The final takeaway is not that energy explains everything. It's that energy explains why explanations work. Because the universe keeps its books honestly, patterns can persist, laws can be discovered, and understanding can multiply. Without that consistency, science itself would be impossible. Energy is the quiet agreement reality makes with itself. Change is allowed, but it must balance. And because of that agreement, there is motion, time, life, curiosity, and the universe capable of being understood at all.